In the world of CPLD and FPGA, there are two types of logic that we use, procedural and combinatorial. Over the next two lessons, we will explore what these two types of logic are and how to implement them in a CPLD. In this lesson, we'll start by learning about combinatorial logic. In the Introduction to Digital Electronics course, we saw many different types of logic gates like the AND, OR, NOT, XOR, and other gates. These gates are the building blocks of digital logic, and similarly, they give way to combinatorial logic. In the Introduction to Digital Electronics course, we also saw how logic gates were connected to ICs like these on your screen, and that by connecting wires to the ICs, we could use these logic gates in our circuits. But with combinatorial logic inside of a CPLD or FPGA, you are given the power to define which gates you are using where, and which pins of the CPLD should connect to inputs and outputs of your combinatorial logic. To show how this works, we'll implement a Boolean algebra equation inside of a CPLD. Let's use a simple equation, z equals a or b and c. If we turn that into a logic diagram, it would have two logic gates as you see here, an AND gate and an OR gate. And the equivalent input to output truth table would look like this. So now let's go to the theory section to implement this as a project for a CPLD inside Quartus 2. First, we'll use the New Project wizard to make a new project. I'll save it in the FPGA folder on the desktop as Lesson 4. Also, the name of the project will be Lesson 4. We'll be using the MAX 3000A part EPM 3032 ATC 44-10. Click Next, Next, and finish the project creation. We'll need to add a new VHDL file to the project, and now we're ready to put in some VHDL code. First, we need to include the IEEE library and the standard logic library. After that, we'll define the entity, which is called Lesson 4. The port for this entity includes 4 elements, 3 inputs, button 0, button 1, and button 2, and 1 output, LED 0. I've added comments to make it clear which input or output is connected to which pin on the CPLD. And then we can end the entity declaration. Next, we need to build the architecture. I'll name the architecture RTL, and then we begin it. Remember, we want to build this logic diagram in VHDL code. To do that, LED 0 will be equal to button 0, or, then in parentheses, button 1 and button 2, close parentheses. Then we end the RTL architecture. Like other coding languages, VHDL has what is called an order of precedence for operators like AND, OR, add, subtract, or anything in parentheses. If a logical or mathematical statement is in parentheses in VHDL, like button 1 and button 2, it will be evaluated first, followed by anything not in parentheses. So that's the code. Let's save the VHDL file and compile the design to make sure everything is correct. Every once in a while, you will make a mistake while building VHDL code. When that happens, Quartus will blurt out a lot of red text errors. The easiest way to debug these errors is to scroll up the compile log and see what the first error is. In this case, a semicolon was expected near the word architecture. And that's completely true. I forgot to put a semicolon after end lesson 4 to close out the entity declaration. So we'll compile it again, and this time everything goes smoothly. Let's open the pin planner and assign each of the button input and LED output pins to the pins we defined earlier in our code. Then we'll recompile the design and go back to the pin planner to make sure that the locations match the fitter location. And now our CPLD project is ready. We just need to build up the hardware schematic. The schematic for this circuit starts out with the power regulator circuit, which takes a 9-volt input from a battery into an LM317 variable voltage regulator that has 2 resistors, 240 ohm and 390 ohm, that set its output regulated voltage to 3.3 volts. 2 bypass capacitors are used on the input and output of the voltage regulator, as well as a resistor and LED to be used to notify that power is good. The next part of the circuit are the CPLD connections. All VCC pins connect to the regulated plus 3.3 volt and all GND ground connections connect to the circuit ground. LED 0 and a current limiting resistor connect from pin 22 to ground. Button 0 connects from pin 23 to power with a 10 kilo ohm pull-down resistor on the pin 23 side. Button 1 connects from pin 25 to power with a 10 kilo ohm pull-down resistor on the pin 25 side. And button 2 connects from pin 27 to power, also with a 10 kilo ohm pull-down resistor on the pin 27 side. And there we have our completed hardware schematic. Now let's go build it up. First, let's look at all the parts that are used in this lesson. We start with the jumper wire kit, the components kit, and a breadboard. The specific parts from the components kit are the CPLD breakout board, LM317 voltage regulator, two 10 microfarad capacitors, two 470 ohm resistors, a 390 ohm resistor, a 240 ohm resistor, three 10 kilo ohm resistors, two red LEDs, three push buttons, and a 9-volt battery connector. And now let's build the circuit. To build the circuit, first we have our breadboard. We connect the power and ground bus lines on opposite sides of the breadboard together, followed by connecting the 9-volt battery connector. And now we'll build the circuit using a part-by-part time lapse so that you can follow along. First we start with the power regulation circuit, then we move on to the CPLD breakout board circuit. With the circuit construction completed, let's bring out the JTAG programmer, laptop with lesson 4, and a 9-volt battery to test things out. First, connect the 9-volt battery to power the circuit, and the JTAG programmer to the CPLD breakout board. Then connect the JTAG programmer to the laptop. Using the Quartus 2 programmer tool, add the lesson4.pof and start the programming process. And when it completes, our code is now on the CPLD, and let's test out the truth table to see if our combinatorial logic works as we would expect. As I run through the different combinations found in the truth table, you can see that the LED output lights up just as the truth table tells us it should. Hooray! VHDL offers most of the basic logic gates that you can think of, like AND, OR, NAND, NOR, XOR, XNOR, and NOT. These can be used in combinatorial logic to build any digital circuit that you can think of, provided it can fit into your CPLD or FPGA device. Another very useful tool inside of Quartus that you can find under Tools, Netlist Viewers, and it's called RTL Viewer. After you've compiled your design, you can view the netlist RTL, and as you can see, it is basically showing you the logic diagram that we used VHDL code to make. This RTL viewer lets you verify that the VHDL you write is synthesizing into the logic elements that you wanted. While logic gates are a large part of combinatorial logic and can be used to create many useful things, like this 3 to 8 demultiplexer, there's another type of statement in VHDL combinatorial logic that is very useful. It's called the when-else statement. This is similar to the switch statement in most other programming languages, where when an input has a certain state, in this case I, a correlating output should be set. As another example, here is the logic symbol and diagram for a multiplexer, and similar when-else VHDL code to implement it using combinatorial logic.
All parts in this online course were provided by the Gadgetory. Visit them at gadgetory.com/pyroedu.
After learning about combinatorial logic, next comes what is called procedural logic. This is where things get very interesting as we will be adding a clock input to our circuits.